1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I start at 62. It's going to change by -9 every time, so that's 53, 44, 35, 26, 17, 8, -1, -10, -19, -28. So one thing I've done is I went the full 10 seconds. I ended up where I expected to be, so I've done something right. I know I'm going to change direction somewhere between 6 and 7 seconds. As a matter of fact, closer to 7 seconds, because that's closer to 0 than the 8 is, which supports what I have over there. Now, I wrote 6.8 and put the bar over the 8 because it repeats. If you just want to write 6.9, yeah, that's fine. I'm less picky about rounding on tests and quizzes.
Where did you get the -9?
In probably part A or part B, it was find the acceleration. And so it was already found. So you find the acceleration using this formula, except you do it for the entire trip. Because I told you the initial and final velocities and I told you time. I told you this information for the entire trip.
Okay.
So that's where it comes from.
Okay.
Have I talked about how I write the tests? All right. I have all the tests listed out by semester. I take the cursor, I close my eyes, and I move the cursor up and down, and I click. That hopefully will click on a folder. If not, I just keep going until I actually click on a folder. When I click on the folder, that's my starting point. I then start going through for the questions that I like. I change the numbers and keep going. Some of the questions are just completely horrible questions, so I never should have asked them. They get thrown out. And other questions that I have a moment of inspiration or watching TV, something strikes me and think, oh, that would make a good question. That comes in, and that's how the test evolves over time. And sometimes I think, I'm tired of the same old questions. Surely everybody has looked at these questions already and know how to do them. So why don't I just come up with something out of left field? And the other evolution of tests is there's certain type problems that become more and more complex as I go. Eventually I go too far and it becomes very clear that I should never have gone there, and then I start cutting back. So who knows where we are in that cycle for a particular problem. And hopefully you don't get one of those tests where I later regret the question I asked. But the general philosophy is that everybody misses a problem and probably does a better question.
I have another question. It was on our last mastering set. I can show you.
Yep.
But it's only covered in part C.
Part C, magnitude of the normal force that's on the scale. Oh. All right, so this is the person in the elevator,
Yeah.
riding up and down. He's going down.
Yes.
Right. While you're standing on a scale, what are the forces acting on you? I think somebody almost said it.
Gravitation.
Force, okay, and
Wait.
same thing. Weight is a specific type of gravitational force.
Normal force?
Yeah, those are the two. Unless he's banging against the walls or the ceiling, I mean, it's just basically those two forces. Now, what's exerting that normal force on him?
The scale?
Yes. What is exerting the weight on him?
Acceleration due to gravity.
What object? Yeah, the planet. So those are the two forces involved. So I got my elevator, I got the scale, he's standing on it, the forces acting on the person, we have this normal force acting up and weight acting down on him. So if he is accelerating upwards, this force has to be bigger than this force. If he's accelerating downwards, the weight has to be bigger than the normal force. If he's in equilibrium, they're equal. So in that problem, he starts up high, and I think he accelerates for 2 floors, and then it's constant, and then he slows down.
Yeah.
So if he's going down and speeding up, in which direction, so that's his velocity is down. If he's speeding up, in which direction is his acceleration?
Say that again.
Positive.
If he is speeding up and his velocity is down, in which direction is his acceleration? So when acceleration and velocity are opposite, he speeds up?
No, it's the same.
Same. When you speed up, acceleration and velocity are in the same direction. So at the beginning, he is speeding up. His acceleration is down. So in the beginning, his weight is bigger than the normal force. Then he hits equilibrium for a number of floors where he's going down at a constant velocity. Acceleration is 0. They're equal to each other. And then he slows down. One hopes in an elevator that when you are going down to the first floor, you do slow down to a stop. So at that point, he is slowing down. In which direction is his acceleration?
Opposite.
Yes. You were just ahead of your time before.
Right.
So their velocity, acceleration, opposite directions, slows down. So at that point, his acceleration is up. So as he's slowing down, his normal force is bigger than the weight. Since this is the normal force acting on him from the scale, this is the force that he's exerting on the scale. Newton's third law, the scale pushes up on him, he pushes down on the scale. So we've got this normal force that he exerts on the scale. This is what the scale is reading. So in the beginning, the weight is bigger, then this will get something less than his actual weight. At the end, when he's stopping, this will give, the normal force has to be bigger, and so it'll be something more than his weight. And you have experienced this probably, I suspect I'm the only one who's actually stood on a scale in an elevator just to test this. But as the elevator is going down, when it stops, I think most people experience that, you know, that you got that extra force going down. If you are on a scale, that extra force would cause that scale to go higher than what your actual weight is. Or that when it just starts out, when it's going down, when it's just starting out, you feel slightly lighter than normal. Well, in that case, because the force you're exerting on the floor, which is equal in magnitude to the force the floor exerts on you, is a little bit less than it was. And if you haven't gone into an elevator with this analog scale, you've just missed out on one of the good things in life. Then, if you're in one of the scouts, you get your nerd badge. Wear it proudly. All right. There was actually, so in this particular question, though, what was part C again?
Your ranking greatest to least in magnitude of normal force.
Okay, so that would cover that.
Yes.
Did I do the normal force he exerts on the elevator?
Yes.
And what is the normal force he exerts on the elevator?
Doesn't
0.
Right. He has to touch it to exert the normal force. All right. Any other questions on this? Genesis? Did you have another question?
Yeah, I just kind of want, so when he's slowing down and going down, the weight is, or is it the normal first?
When he's going down and slowing down, acceleration is up, which means that the upward force has to be bigger than the downward force. The net force is in the direction of acceleration. So in this particular case, when he's going down and stopping at the first floor, since acceleration is up, The normal force is bigger than the weight. The scale is going to be more than its weight. Other questions?
On a different question, I have a different question now.
Okay.
It's like a box. It has a picture with it. It's this
That one.
and that, and I don't understand this place.
Okay. Friction's here. The friction anywhere else? But actually, the friction doesn't matter in terms of displacement. So, this is one of the things I talked about. The problems get more and more complex. If you look at the early ones, it's ball being thrown into the air, but over time it has evolved. And I got friction here. It starts out here, going up the ramp. It's going to hit some point at time D. It's going to stop, come back down, go down, come up to here, and then come back and stop somewhere around here.
In the middle of that slant.
Of this one?
Yeah.
Okay, it'll stop somewhere there. Yeah, straighten the whole thing, go away. So up, back, down, up, back, and then stop. All right. When trying to determine where an object is, if I just said that, hey, there's a restaurant giving away free food, it has a position of 5 meters, 45 degrees. That is not very helpful, because 5 meters from where? So a lot of communication deals with giving a reference point. It's 5 meters away from here at, goes due northeast. That will tell you where it is. So the difference between position and displacement is what you're using as a reference. So position here is about where is the origin. Just for the sake of some silly mnemonic, origin, position, got OP, Ocean Pacific, PO, put out, or whatever form you want to do with that one. O represents a full bladder, and you need to pee. The sillier it is, the more apt you are to remember it, according to some. All right. So in that case, I think the origin was somewhere around here.
The origin, it was the second slant in the middle.
Second slant, this one over here. This one here?
Yeah.
Oh, in the middle there?
Yeah.
All right. That doesn't sound healthy. So I think in that problem I said to the right is positive, just so that everybody's using the same language here. So anything to the right of the origin is positive position, anything to the left is negative. All right. Does not seem to be an issue for you. Displacement has a different reference point. Displacement cares about where did you start. That was the Usain Bolt. When Usain Bolt got back to the starting point in the track, his displacement was 0, his average velocity was 0. Whereas I hadn't gotten there yet. I had a greater magnitude of average velocity. So here, all we're doing is we're shifting basically our reference here and shifting it to where we started. So since we started there-ish, this is now our reference. So anything over here where I have positive displacement, anything over there I have negative displacement. So it's as if you had a number line, a classic number line. I got 0 here, I got a positive side, I got a negative side. So for origin, I'm just moving it so that this is lined up with my origin, and for displacement, I'm moving it so that this is lined up with starting point.
Okay. Even if the box was already moving at A?
Correct.
Okay. So, what did I say? So, A, B, B, and B, C? Is it, wait,
So so this was C when it gets back to the starting point. So if I'm looking at how do I actually communicate it? A and C is at the starting point, displacement 0.
oh.
If I'm to the left of that, so I am in the negative displacement from after A, from A to, in essence, C. Or in the form that you were looking at, it was from A to B, B to C.
So position is from where the origin is, and then displacement is where it starts.
Based upon the starting point.
Yeah.
Yeah.
Okay. That makes sense.
SD. Sexual dysfunction.
Standard definition.
There we go. Standard definition. Standard deviation. San Diego. Detective Sergeant. Sid.
This law. This law.
Sorry, one more time.
Say this law for my sake.
Ah. Other questions?
Can you go over the distance and objectives?
All right. By the way, on the plus minus 0 exercise, which is what the problem to which she was referring, you'll have position, displacement, velocity, acceleration. None of them will be the same all across the board. If you do that, if you give me the exact same answer across the entire row for 2 of them, I will give you credit for the one that you get most points on, and I will give you nothing for the other one. So, if you're feeling like these two look like I think these two are identical, think again, and at least make one change there. Get something. Okay, distance traveled. So I've got a vehicle. Let's take the one that's traveling at 62 meters per second to start with. It's going to go down, turn around, it's going to end up cutting back. So at the beginning it's going 62 meters per second, at the end it's going negative 26 meters per second. No, negative 28. I know it changes directions because it goes from positive to negative. It changes signs, changes direction. So when I'm talking about displacement, it's where I am relative to where I started. So after 10 seconds in this problem, my displacement is from where I began to where I ended. And I was going to do blue for contrast. So my displacement from where I started to where I ended, that is my displacement. I can find that by average velocity times time. If my acceleration is constant, I can find my average velocity by just averaging the beginning and end. (34/2). So my average velocity is 17 meters per second. I traveled for 10 seconds, so my displacement, it's getting worse as I go. All right. Is equal to my average velocity times time, which is 17 meters per second, times 10 seconds. So I end up 170 meters from where I started. That's not even good. Okay. So I know, though, that I traveled farther than 170 meters because I had to cut back. So the question is, how far did I actually go? Well, I traveled from here to here, and I traveled from here to here. So the distance is just the sum of those two scalars, those two distances. Technically, I have a positive displacement from here to here. I have a negative displacement from here to here. But when I'm looking at distance, I don't care about cutting back. If you think about a car, if I go to the store and come back, I have traveled a certain distance, and my odometer is going to give me a different number. If it were giving me displacement, when I go to the store and come back, it should be 0 because I'm back to where I started. Which sounds like a fun thing to just throw in as a freebie for those of us who think that would be cool. There you go, $1 million idea. You can have it. So, the trick on the distance problem is figuring out how far does an object travel to here. That's the hardest part of it. Well, I know it started at 62. This is a turnaround point, so it's going 0 meters per second. I already know how long that takes because we solved that problem earlier. This particular one, that's why I'm using the same numbers, but there we go, 6.8 repeating seconds. So it takes 6.8 repeating seconds to stop. So to figure out how far, I'm going to do the same process here, except for the fact that I'm not looking at the entire journey, but just part of it. Well, my average velocity, well, I averaged those two numbers, 31 meters per second.